Hello everyone, I am Wim Verbakel. I'm as well a firefighter from Belgium. And I'm going to talk a little bit more about gaseous hydrogen and how we can react to incidents with gaseous hydrogen during incidents. We're going to talk about how it is used as a fuel on vehicles, how it is stored in vehicles in hydrogen cylinders, and the incidents we may come across, how we can measure hydrogen, and as least how we can refuel vehicles with hydrogen. We also see the ISO symbol. Matthias also talked about it. We can see that hydrogen is lighter than air. It's compressed, and in this case, we can see that it's a dual fuel application with diesel. To start, here you can see a few vehicles that are possible. It varies from regular cars up to heavy machinery, trucks, etc. First of all, these vehicles can be propelled with a fuel cell. And in case of a fuel cell, it's in fact an electric vehicle, and the electricity is produced in a fuel cell. In this fuel cell, you can see one here, there is a chemical reaction between the hydrogen gas and the oxygen gas from the air, and the reaction product is just water, and we get electricity by this reaction. The hydrogen is stored between 350 to 700 bars in the tanks. We can see a few tanks in this car, 3 tanks in total. And this is a fuel cell car, so we have a fuel cell, and the fuel cell generates electricity, and this electricity is buffered in a small lithium-ion battery, and the electric motor propels the car. There is also a medium pressure, and that medium pressure we can find this between the cylinders and the fuel cell, and the fuel cell itself works around 1 to 4 to 2 bars in pressure. A few examples of fuel cell vehicles. We can see just small cars. We can see a city sweeper used in inner cities to sweep the streets without emissions. We can see garbage trucks and a person bus, for example. We can also use a dual fuel system, and dual fuel is in fact a regular diesel engine that is converted to run on the combination of diesel and hydrogen. We do this so we can get a decrease in fuel consumption and also lower emissions. We can see here an intake manifold of a diesel engine that is fitted with hydrogen injectors to let the motor run on the combination of diesel and hydrogen. A few examples. We can see a regular truck that is converted to run on the combination of hydrogen and diesel. And here also a tugboat that is converted. Excavator can be converted, and as well a straddle carrier, like we can see here. We see this as a way to for the energy transition. This is a way to equip heavy machinery with motors that can run on less fuel and less emissions until these can be made fully electric or even in other ways. There are 4 types of gas cylinders we can store the hydrogen in. We can see first these type 1 and type 2 cylinders. Type 1 is just a regular metal cylinder. Type 2 is a metal cylinder with structural hoops, composite hoops, to provide structural integrity. These 2 types are not used in vehicles. When we take a look at the vehicles, we see type 3 cylinders and type 4 cylinders. A little bit more about those. Type 3 cylinder is a composite cylinder with a metallic liner, and it can be used up to 350 bars of pressure. It's available in different volumes. You can use it for fast refueling, and it's mostly used in trucks and buses. The type 4 cylinders are fully carbon with a plastic liner. These can be used up to 700 bars of pressure. They are lighter. They can be up to 70% lighter compared to the type 1 metal cylinders. And they are compact, and therefore they are mostly used on cars. They can be used for fast refueling, but it's important that the hydrogen needs to be cooled before it can be fueled into the car. As Matthias told before, the cylinders are protected by a thermal pressure relief device. This is a device, a valve that opens at about 110 degrees centigrade. The flow of the blowdown is determined by the diameter of the TPRD and the pressure in the tank. There can be one TPRD on a tank, but there can also be multiple. So how a TPRD works is a bit comparable to a sprinkler head. There is a small glass tube inside the valve, and when it breaks at a certain temperature, it will open and it cannot close. It will blow down the complete tank. We can calculate how long that blowdown process takes. For example, a tank we commonly see in vehicles like this. We have a 50-liter tank, a 2 millimeters diameter TPRD at a pressure of 700 bars. And when we look at the graph, we can see that blowdown will take about 2 minutes from full tank to empty. So on most regular cars, the blowdown will be to the downside of the car, downwards release. But this is not always the case, especially when we go to the bigger vehicles and heavy machinery. It can be either direction, so it's something we need to take in mind. What is our incident strategy? First of all, we use the basics we use for every hazmat incident. So we maintain a distance of at least 50 meters. And when there's a significant fire hazard or in unclear situations, we maintain distance of 100 meters. And it can be up to 500 meters if there is explosion risk, for example, with a tube trailer. We establish a parameter, we evaluate the outcome, the possible outcome of the incident, and we consider the risk of our own personnel on site of the incident. We try to stay upwind. We use a thermal imaging camera and explosion oxygen meters during the incident. This is a small example of a graph to determine the effects of an explosion. So in this case, we use a tank with a volume of 60 liters at a pressure of 700 bars. And we can see that in case of an explosion, we have noise disturbance up to 75 meters. We have collapse of walls, debris and 1% hearing damage up to 13 meters. And lung damage and 1% fatality up to 1.65 meters. Keep in mind that this is in case of a physical explosion, so there is no fire involved in this case. Other general principles, like said before, we make use of a thermal imaging camera to detect the leak and the fire because it will be difficult to see just with your eyes. We will not approach a venting tank. We try to avoid ignition sources, and we try to ventilate in a safe way in case of a leak in a confined space. If there is a fire, we cool the surroundings, but we won't try to extinguish the hydrogen flare. That's just comparable to other incidents with gas leaks. If there is an incident with a car, we try to approach it sideways. Sideways is the safe zone around the car. We will look up how we can secure the car. We can use a crash recovery system or emergency response guidelines. And we need to think about the venting directions and keep in mind that the vehicle can be tilted. We try, if we have a car on fire, we will try to extinguish the fire and cool the tanks. Keep in mind that the TPRD can be activated and that there will be vent flames from the vehicle, and the length of those flares can be determined or are determined by the TPRD diameter and the pressure in the tank. If there is a flare, we won't try to extinguish the flare, we will just extinguish the vehicle and cool the tanks if that's necessary. But in most cases, the pressure will be released very fast if the TPRD is opened. You can also see in this picture that with just visible sight, the flame is not completely visible, but with the thermal imaging camera, it's very good visible. In case of a hydrogen leak, there will be a very loud noise because we have to deal with very high pressures. We won't try to approach the venting tanks. We will avoid ignition sources. And if it's a confined space, keep in mind that an explosive mixture is certainly possible and you need to try to ventilate in a safe way. If there is a car accident, there could be leaks, especially when there's a big crash. There are electronic valves on the tanks that will close if the car detects a collision. But you need to be sure about the integrity of the tanks. There could be hidden damage. And if it is a fuel cell electric vehicle, you need to keep in mind that there are also high voltage parts and a lithium-ion battery on the car that could be damaged. Also important, after the incident, we need to support the towing company and tell them with what kind of vehicle they have to deal with. Measuring hydrogen. This is a kind of meter that is often used in fire departments. It's a regular explosion oxygen meter, XM 2500 with a catalytic cell. Important to know is that the correction factor for hydrogen gas is 1, so that's easy for us. But there needs to be at least 14% oxygen in the air to make a correct measurement. And the CO, the carbon monoxide cell, is cross-sensitive for hydrogen. Thus we can use the carbon monoxide sensor to measure even small quantities of hydrogen in the air. Important to know is that the infrared cell or even the PID does not detect hydrogen. So those cannot be used during an incident with hydrogen. Refueling of hydrogen vehicles, we have two big possibilities here. We have a stationary refueling station with maybe its own production or a pipeline or tube trailer delivery. Or we can have a mobile refueling station, a container unit that is connected to a tube trailer, for example, for large construction sites with heavy equipment that runs on hydrogen. Refueling can be done on 350 bars. So for the vehicles that work on 350 bars, it's just a simple connection between the buffer and the tanks on the vehicle, and it will fill itself according to the principle of communicating vessels. For the 700 bars, the buffer is at higher pressure, up to 1000 bars, and the hydrogen needs to be cooled beneath minus 40 degrees centigrade to protect the cylinder during the refueling process. Communication between the car and the refueling station is also necessary in this refueling system at higher pressure. So this is a small example, a schematic example of those options. So we have fueling station at a lower pressure that goes from the buffer directly to the vehicle. And when we have a refueling station at high pressure, we see that it goes to a chiller, and into the car. Refueling systems have a lot of safety systems. Those are, for example, flame detection, gas detection, emergency stops, and even a blow-off installation in case of an emergency. When we take a look at our incident strategy during a leak in a refueling station, also again important, make use of your thermal imaging camera and detection devices. Involve external expertise. This is a very important step. These are complicated systems, and we as a fire department don't have all the knowledge that may be needed to deal with these systems. Determine the possible risk of the incident. Determine a safety distance. Use the available safety features in the refueling station, and think about possible escalation of the incident. In case of a fire in the refueling station, again, make use of your thermal imaging camera because the flares won't always be visible, certainly in daylight. Involve external expertise. Try to extinguish the fire to reduce the radiation to the tanks, but don't extinguish the hydrogen flares. Keep in mind that if there are tubes in the refueling system or even a tube trailer, those don't always have TPRDs, so it may be necessary to cool the tubes. Try to do this with, for example, a monitor, so we can also evacuate our own personnel, preferably to up to 500 meters. This was my presentation. I want to thank you for your attention, and I give the floor to Gustav, who will give you an example about the XVR case.